So, welcome. Today we would be starting up with our next version, which is on multilayer perceptrons to deep neural networks. And while in the earlier lectures we have all studied about what neural networks are, and we have done a few lab sessions as well on and that was about just understanding neural networks from a classification point of view. And now where the extension comes down in perspective of visual computing is that here, in contrary to what we were doing in the earlier classes, was that in the earlier classes while we were using feature extractors and feature descriptors, which are hard coded functions over there in order to describe an image, and then we extended all the summary or the synopsis coming out of each of these feature descriptors together into a classification framework using a neural network. On the contrary, today when we are going to do it, so here is when a neural network itself has to come down to be an end-to-end learning framework, which means that input to the neural network itself is an image, while the output from it is still a classification output. So, it can be a classification output, it can be a regression output, any of these things which come out. So, where we would start down very specifically is that here we are going to look into a multilayer perceptron, and that is our starting point, and from there eventually we will enter into what is known as the deep neural networks, and then what are the existential criteria and how they work. So, effectively we would be doing a basic review of the perceptron model and the perceptron learning rule once again, and then entering into the multilayer perceptron. From there we enter into something called as the signal flow graph representation, and this model of a signal flow graph is how is my input and my output related and what happens during the learning phase. And this is a quite critical part over here, since in the last lecture and the lab which we had done, so you were introduced to the concept of error backpropagation, and from there we had a gradient descent based learning rule. Now, what exactly happens in telling this as a error backpropagation and why it happens the way it has been named, and what you have seen down in different snippets of code is what we are going to explain you through this signal flow graph representation. Following that is a very important aspect about gradient calculation, and that is to show down what happens within these functions, and whether the gradient is just for the classification cost function or does it need to exist throughout the network. And that is where we will enter into something called as an existential criteria for the network to exist, and all other transformations and cost functions also to exist, and then eventually go down to the learning rule, and from there we more or less come down to an end of what happens with these kind of deep neural networks. So, as with a simple neuron model, so just to do a brief recap of what it was. So, say that there were 3 inputs over here in the earlier case last week when we were doing it. So, these were given down as features, say 3 different features, but here now these are no more 3 different features, but these 3 can be 3 pixels. So, you can consider just 3 pixels in an image and give them as an input to the pixel in its own way, or it can be even say for a given pixel in colored space, if you have one particular image in RGB color space. So, each component itself is represented as one independent scalar value. So, your x1 can be the red value of a pixel, x2 can be the green value of a pixel, x3 can be the blue value of a pixel, and accordingly, so per pixel basis you can make some sort of a decision coming out as well. So, let the decision associated with a particular pixel over here be p hat, and now with the simple neuron model what would happen is that we will have a weighted combination of these inputs going down to a neuron, and from there add down a bias, take a summation out over there, and this summation is what has this form. So, it is w naught plus w1 x1 plus w2 x2 plus w3 x3, where each of these weights w1, w2 and w3 are 3 weights associated with each of the 3 values x1, x2 and x3, and w naught is what is called as the bias, or the w naught can also be written down as 1 into b, where say b is the weight over there and the constant input to this particular edge over there is what is 1. Okay. So, in its linear algebra form, which is in its matrix representation, this is the form which you would be getting now. So, you get y is equal to the inner product or the dot product of 2 matrices. One of them is the weight matrix, where you have the weights and the bias taken together, and the other matrix is a column matrix over there. So, that is why it is x comma 1 transpose, where x is this scalar arrangement So capital X is basically a matrix arrangement of these 3 scalars which you get down over here. Now, having taken all of them together, the next part is to apply some sort of a nonlinearity, and that is the FNL nonlinear function which you get down over here. And these nonlinearities can have multiple different forms, and we consider these 2 forms over here. The first form is called as the sigmoid, the second one is called as the tan hyperbolic nonlinearity. And to do a very basic recap, so you remember that in sigmoid what happens is that as the value of y tends towards plus infinity, this value tends towards plus 1. As the value of y tends towards minus infinity, this value tends towards 0. And on the contrary, with a tan hyperbolic, what happens is as the value of y tends towards plus infinity, you get a value which is saturating at plus 1. As the value of y tends towards minus infinity, you get a value of this nonlinearity which is at minus 1. So, taking these 2 together is either one of them you can be using now, and based on whichever you are using, your p hat's value will appropriately be decided. So, if your p hat has the nonlinearity associated as a tan hyperbolic, its value will be in the range of minus 1 to plus 1. If it has sigmoid as nonlinearity, then its value will be in the range of 0 to 1. And this was the simple perceptron model which we are doing. Now, from taking down a perceptron to getting into a neural network formulation, which is that given I can have multiple kinds of inputs over there, it can be different kinds of scalars over there, and I can map it down to again a different group of scalars. So, maybe my first prediction over there is what is called as p1 hat, and this will be the form of representing everything to my p1 hat. Now, note over here that as we had also discussed in the earlier class, is that these weights are no more with just one subscript, but there are 2 subscripts which you see with these weights 1, 2, 1, 1, 1, 3. Now, the reasoning behind these weights is that the first subscript is to the target where it is mapping. So, the output over here, say I have x2 which goes to y1, and that eventually maps down to my target which is called as p1. So, my first subscript is going to be the subscript of the target, my second subscript on the weight is the subscript of the source from where it is connecting, and that is the nomenclature which we are following. Now, if I arrange all of these weights W11, W12 and W13 in a row matrix form, then that is what is written down as this bold W1, which is the matrix given down in the equation. Okay. Along with that, I have my scalar value which is my bias W10 or B1. Okay. And accordingly, x is my x comma 1 transpose is my column vector which comes down, and this gets my inner dot product and then my nonlinearity applied. Similarly, if I take down my second neuron on the output side of it and feed it appropriately, so I would be getting down this second part of the partial network coming down and my group of equations which represent that. Now, projecting onto this and going out similarly, so I can have my xjth neuron connected down to my ykth neuron with a weight which is called as wk comma j, and then put a impose a nonlinearity on top of it, and then taking all of them together, this is a particular form where I get where w subscript k is a row vector which has a size of so the number of connections over there will be basically from 1 to j, which is because that is the total number of x's which you have over here. So, for this combination, this is a particular kind of an output relationship which we see. Now, if you look into this matrix of weights and biases which are combined together, then you can see down that all of these outputs which I see y1, y2 up to yk. So, if I take all of these together and just concatenate them, so I arrange them in a column form in a column major format, which is that it just has k number of rows and just one column over there. Accordingly, my bias B that can also be arranged into a column matrix over there. Okay. So, these are the 2 matrices which we see over here, and then my W, each of these W1, W2 up to Wk, they can also be stacked one on top of the other because each is independent of the other one, and now that would give me some sort of a rectangular matrix. Now, if I clearly look into it, then my total transformation equation over here can be written down in terms of just a matrix multiplication. So, this will be a matrix multiplication of my weights W's and B bias, these 2 kinds of matrix with the input over there which is arranged as a matrix, and then that gives me an output matrix over there, and this output matrix is a column matrix. My input matrix is also a column matrix. So, that is my y, and then I have a nonlinearity applied on a matrix, which means that each element of the matrix is appropriately subjected to the nonlinearity over there, and then taking all of them together is what I get down as my target output. So, this was my very basic understanding of how a neural network works down as such, and then this was what we had done with the multilayer perceptron in the last class itself. Now, again going down a bit more into the revision part over there. So, my error in prediction, how it was defined was that if I have one of these predictors P1, then I get down one value of a scalar error. For another predictor P2, I get down another error which is E2. Now, if I have an array of these predicted variables over there, then I cannot keep on calculating each and every error singly, because in that case I do not get a consolidated knowledge about the total network as such. So, in order to do that, what we do is we find out what is the Euclidean error over there. So, a Euclidean error or the total error of the network is basically a scalar value, which is the Euclidean norm or the L2 norm of my of all my predictors. So, whatever is my actual ground truth, which is P, and my predicted value P hat, these two matrices are subtracted, and then you take a the amplitude of that or the L2 norm of these two subtractions. So, and given that, the next part is that you will be doing a backpropagation in order to learn down your algorithm. So, the idea is that you have these successive bunch of observations and predictions, and what is the ground truth. So, if x1 is a matrix of all of these scalar x's over there, and one of these samples is x subscript 1, then the ground truth corresponding to that is what is p subscript 1, and at any given point of time when you feed the whole data x subscript 1 through your network, you would be getting down a predicted value which is p hat subscript 1. Okay. So, similarly, I take my input sample as x subscript 2 and I feed it forward through my network, I get a p hat subscript 2, okay, while the actual ground truth over there is p2. So, I keep on doing this together, and then for my nth sample, which is my last sample in my training data over there, as I feed my last sample through my network over there, my output is Pn hat, and then my actual ground truth corresponding to that is Pn. So, together if I have all of this, so what you would see is that there comes an error which is there for each sample. So, for my first sample, second sample, third sample, till my nth sample, I will be getting a different value of error. But can we give some sort of a consolidated error for the network in terms of its performance across all of these training examples which we are taking down? And for that reason, we devise another metric which is called as the cost function of the whole network in terms of its weights. Now, that is what is defined as JW over here, and that is a summation of the Euclidean distance between these predicted P and the actual observed and the actual ground truth of these P's which are supposed to be there. Now, if you look into this cost function over there, what we said is that JW is your cost function, where these varies in terms of your weights which are W's. Now, what comes down definitely in somebody's mind is that why is it varying with respect to something called as a W? And the reason is that these W's are weights which are the only thing which now would be guiding down and accordingly manipulating what happens to your predictions over there. So, because there is not anything else on which it can change. See, my input x is constant. So, that will be different number of samples, and across samples and across between two samples it will be a different value, that is always known. But when I am training across an epoch learning, which we had done studied in the last classes as well. So, when you are training across epochs, what happens is every epoch you are going to set the same sample over there. The only reason why the prediction value of putting down the same sample, so say at my first epoch, which is my epoch number 0, over there I put down x1 as my sample and I get down a predicted value p1 hat. I do all my updates and everything, and then comes to my second epoch, which is epoch 1. In my epoch 1, I put down x1, I would be getting down a different value which is p1 hat, but p1 hat at the epoch 1 is very different from p1 hat at epoch 0. And the only reason why this was changing is within the network the only variable component is weight which changes. So, that is the reason why we would write down this cost function in terms of our weights itself. Now that I have my cost function written down in terms of my weights, my final point is that we need to come down to a point where to a point in the weight space such that my argument of these cost functions is minimum, or as I keep on the point is that if we keep on changing the weights, there will be one particular combination of these weights such that my error is minimum, and that is the exact one which I would like to achieve. Now, and how that is achieved is through something called as the gradient descent learning rule. So, in this gradient descent learning rule, what we do is basically that it is an iterative process in which what you do is you start with some randomized assumption of weights in the first epoch, and then say that is wk, okay, and then you compute out whatever is your gradient of the weight space over there in terms of your cost function, and that is del w of jw, and then you weigh it by a factor, an empirical factor which is called as eta, or also known as the learning rate. So, what this controls is that your gradient of this error function over there del w of jw, that can have any range of a value. Now, if the range of, say, these w weights are in a range of 0 to 1, and then say my del w of jw is in a range of 10 power of minus 9. So, the rate at which it would be updating or impacting the value of w is going to be very less, and in that case this eta factor over here comes to your rescue, because what you can do is you can set a eta factor, say 10 power of 6. So, if you multiply a value in 10 power of minus 9 to a value of 10 power of 6, that will give me a value which is in the range of 10 power minus 3, and that value is something which will actually be impacting significantly how the value of w is changing over there. So, this learning rate basically is a way of mathematically modulating the gradient over there such that we have a value of this error and the gradient coming down, which will be in some way significantly impacting the change in w, and that is how my w of k plus 1 will be revising at a much better rate than w of k would have if we did not have this learning rate called as eta. Now, given that we have all of this done, so what typically happens within a gradient based learning rule is something like this, that you would be starting down on your first epoch, and then as you change these case, so you will be getting your first value of jw. Based on your jw, you would be calculating your gradient, multiplying that with your empirical constant eta or the learning rate, and then you update your w to w of k plus 1. As you update it to w of k plus 1, you would be getting a different factor of jw, which is jw of k plus 1, and accordingly this keeps on changing and so on and so forth till you are at the final conclusive step over there. Okay. Now, this was one way of trying to visualize our learning in terms of its cost function versus epochs, and this can be a typical graph. So, you would often be seeing that you start with a particular error and your error increases and then keeps on decreasing, or it may so happen that it increases then keeps on decreasing and suddenly again hits a local maxima, it increases slightly then goes down, it may keep on jittering, and these are all aspects about what is happening within the learning itself. So, if your value of eta you can keep your value of eta very less. In that case, what will happen is it will come down very slowly, but it will be a very smooth transition which it will be getting. If your value of eta is very high, then it can start oscillating and jittering over there, and that means that it is basically overshooting the local minima point at every time when it is coming down somewhere closer to the local minima. And these are different issues which we would be tackling down through experimental processes and some more learning experiences subsequently. Now, looking at the same part of gradient descent again in the weight space. So, what we had learnt was that say I start with some random value over there, and this is my point, and if so here what I am doing is typically I am looking into two different plots. So, one is my plot of epoch versus cost function, the other is my plot of weight space versus cost function, and these are two different aspects as such. So, the second epoch, when I update my weight, so it shifts to a different weight vector coordinate over there, and subsequently I have a different cost function value also calculated through it, and subsequently it goes to the next one, then to the next one, and finally to my convergence. Now, if you look into this part of the plot, what you would see is that for any kind of a perceptron model, you would be seeing that the error function over there forms some sort of a wavy structure which quite mimics a egg casket like design, where you have multiple number of crests and troughs present over there. So, as these points of my weights they keep on moving down, they would always be encircling and coming down to my local minima point as soon as possible, and the way it comes down to this local minima is what is my learning which is happening. And also from the last lecture about introduction to deep learning and what happens within this multilayer perceptron and challenges, you did understand that one of the major points is that we can actually initialize a network at any random point over there, and based on that it can start converging and oscillating around any of these troughs, and that definitely means that where it is going to converge is now some sort of dependent on where I started. If I started down in the neighboring one, then it will be in the trough of the neighboring. If say there is no global minima, but everything is equivocal point over there, there is no unique global minima in that case. Now, if we have a unique global minima, then the challenge is obviously that you do not lock into any of these non global minima positions, but rather somehow escape into this from these small trough like regions and exactly converge onto your global minima position. Now, having said all of this, what comes down to our mind is something interesting. So, you have seen that there is for any kind of a given network, if I have 3 different scalar values over there, then I can take in these scalar values and I can predict out one of these predicted outputs over there. Okay. And for a simple perceptron, how it goes down is something of this sort, that I have my weights W1, W2 and W3. I take all of these weights together and then I sum them up, and accordingly I get down my bias also coming into play, and then I map it down to my output over there. Okay. The question is that now that I need to find out my del del W of JW, then what would I be doing? So, in order to solve it out, the best possible way is basically trying to look into something which is called as the chain rule of differentiation, which you have done in your high school mathematics itself. So, what goes down by the chain rule is that we would try to break down all of these into its constituent component. So, the simplest way of doing this is that let us break down this derivative product, which is partial derivative of JW with respect to W, because we cannot directly compute. So, what we will be doing is, so you know that the output of this JW, so JW was a cost function, and that was for our case a Euclidean distance of the predicted output with respect to the ground truth. Okay. So, I do not have any component of x as such directly visible, neither my weights directly visible over there, but what I have is definitely my p hat or p over here, which is my predicted output state. So, I can take a derivative of the cost function with respect to this output. Next is my output is dependent on y through a nonlinear function. Okay. So, that means that I can take this partial derivative of p with respect to y. Now, if I look till the first 2 partial fractions on my right hand side over there, so you can see that del w of JW can now be represented as a product of del p of JW and del y of p. So, together these first two parts over there will give me del y of JW coming down. Now, the next part is, now that I have a del y of JW, I should be getting down another part of the partial fraction, which is partial fraction of these derivatives, which is my del y of del W of y, which is my output of this summation block in my neurons. So, together this is what will help me in getting down my total gradient computation. Now, the first part of this gradient, which is which is some sort of a derivative of the cost function. If you look into the second part of the gradient, then you see that it is a derivative of the nonlinear transfer function. And if you look into the third part of the derivative, that is a derivative of the linear network itself. And these 3 things together are what will be helping me in finding out the gradient part for my whole network in order to learn. So, with this I will end up our lecture for today over here, and in the subsequent lecture we would be starting up with this point on gradient computation, and subsequently going down to how this can be extended for a multilayer perceptron, and then enter into eventually the deep learning and how to train down these deep neural networks, and then what will be the existential criteria. So, with that thank you and stay tuned for the next lecture.